In today's lesson, we're going to talk about timers used in Studio 5000 Logix Designer. So what is a timer? A timer is an operation that can be used to delay the action of an event in your program. Let's say you want to activate a operation, but you want there to be a small delay between when you get an action from a sensor or something to the time that you actually trigger some sort of an output reaction, such as maybe a trapdoor opening or something like that. In this type of an example, you would want to use some sort of a timer in order to control your process. Some of you who have worked with controls before may have some familiarity with the concept of mechanical timer relays. And there's an example of one up here in the top right. A mechanical timer relay can be set up to do a variety of different functions, including an on delay, an off delay, or some other variation of timer actions. And usually they'll have a dial on the front or some way of controlling the timer preset value. Whenever you energize the relay or de-energize the relay, it will change the state of the output for that specific relay. There's different types of mechanical relays, but these work in very similar ways to what we're going to be talking about today, which is PLC-based timers. The biggest difference between a mechanical relay timer and a PLC timer is that the PLC timer can be adjusted inside the software if we want to make the timer take longer or adjust automatically to different conditions, or let's say if your conveyor speed is slightly faster than what it normally is, you can actually have in the program somewhere to adjust the timer set point to affect the action at a different time based on your conveyor speed. Over here we have an example of a timer used in Studio 5000. This is one version of the timer instruction, but most timer instructions available in Studio 5000 look similar in structure. They just change the acronym. Now, whenever you use a timer, and again, it's important to understand that in this particular lesson, we're primarily talking about timers used in Logix Designer using Allen Bradley software. Now, a lot of other PLC programming software will use some variation of timers, but in this particular example, we're only really focusing on Allen Bradley and the Logix Designer variation of timer instructions. Whenever you use a timer in your program, each timer needs to have a unique tag that is a timer data type. You cannot have the same timer data type tag used on multiple timers. Each timer needs to have its own unique data tag. Now, what is this data tag? The data type inside this contains all of the elements required for the timer to function properly. All timer instructions use the same timer data points that we can use within our program or that the timer uses on its own. The first element, called the enable bit, abbreviated EN, is true when the rung is true. So whenever the timer instruction is actually being energized by your rung, the enable is active. You'll also have what's known as a timer timing bit, abbreviated TT. This is true whenever the timer is counting. So usually if your timer is currently counting, So it's, let's say the value you set it to is 5 seconds, and the current amount of elapsed time is going up to that 5-second set point. Then during that time, while it's enabled, the TT bit or timer timing bit will be true. But once the set point is equal to the accumulated or the elapsed time, then the timer timing bit will go off, and the only thing that will be active is the enable bit. And in some situations, depending on what timer you're using, the done bit. So that's the next part, is the done, abbreviated DN. This is the output of our timer. So no matter what type of timer you're using, usually if you're using it in your program, the part that you really care about for your code is going to be the done bit. Then you have 2 integer tags, and these are going to be, first, the accumulated value. This is the elapsed time that has currently passed for the timer. This is abbreviated ACC. Depending on the type of timer you're using, it may count up. Most of the time they do in Studio 5000, but the accumulated value is going to represent the timer's current elapsed time in milliseconds. And when we say milliseconds, that means for every 1 second there are 1,000 milliseconds. So whatever time you want to set the timer to is going to always be in milliseconds. The next element is also an integer. This one is our preset value, abbreviated PRE. This is the value in milliseconds that we've set the timer to, as far as how much time do we need to elapse to affect the action that we want to occur, or activate or deactivate the done bit. Now, we made a comment earlier about how there are different types of timers within the software. So let's take a look at what those are. So there are 3 main types of timers that you're likely to run into when dealing with Studio 5000. These 3 are listed here. The first one is the timer on delay. The acronym for it in Studio 5000 is TON. A timer on delay, similar to how the name suggests, is the timer is energized. The accumulated value is going to increment up in milliseconds until the accumulated value is greater than or equal to the preset value. When this is true, the done bit will be true. If the instruction is made false, meaning that the rung becomes inactive, then if the done bit was active, the done bit will be set to 0, and if there was a value in the accumulated or elapsed value, then it will be reset to 0. The second type of timer is called a timer off delay, or TOF. A timer off delay works very much in the opposite way as the timer on bit, or the timer on timer. When the instruction is true, the done bit is actually made true immediately and will remain true as long as the rung is true. When the rung becomes false, the done bit is still going to be true, but then you're going to have the accumulated value or the elapsed time start to increment up. When the accumulated value is greater than or equal to the preset value, then the done bit will be made false, and the accumulated value will remain the value of the preset. So basically, you'll see where the timer will increment up, and then when reaching the preset, it will freeze at that spot and not increment up anymore, and it will not reset to 0. The final type of timer is known as a retentive timer on, or RTO instruction. Now this works exactly the same way as the timer on. The only difference is that the retentive timer on, much as the name suggests, is going to retain the accumulated value of the timer. It will normally, the timer on delay and the timer off delay, the accumulated value will return to its preset value or its default value. For a timer on, that would be going back to 0. For a timer off, it will be equal to the preset. But whenever you're dealing with a retentive timer, the accumulated value will be frozen at the value it was when the instruction became false. And then when you re-energize the timer, it will count from where it was to continue counting up until either the preset is reached or you activate a reset instruction. So the retentive timer is the only one that you must use a reset tag or a reset instruction to clear the data of the timer. If you do not clear the timer, it will continue to hold the last recorded value for the accumulator, and if the done bit was made true, it will remain true. So you can kind of think about it as a delayed latch instruction where you activate the input and you hold it for, let's say, 5 seconds. When the 5 seconds is up, then the done bit will be made true, and it will only go away when you activate the reset tag. So now that we've gotten a little bit of a familiarity with the different instructions, let's see how they work in action. Here you can see that we've got a simple tank fill operation. On our main console, we have a variety of different controls. So let's get a good look at what we've got. So this first row is a timer on instruction. The second row is attached to a timer off instruction, and the last row is a retentive timer on instruction. I've set all of the presets for each of the timers to 5 seconds or 5,000 milliseconds. In the program, I've just attached these buttons to activate the timer that they're associated with. Each of these timers have their done bit attached to the action of the tank fill. So any time that we reach the done bit, or the done bit becomes active for any of our timers, it will activate our fill function in the tank. The tank is fixed to automatically drain for us. Let's first take a look at what happens when we press the timer on. When we activate the timer, you'll see that the accumulated value starts going up. You can see it on the display here and on the timer instruction in the software. As long as I'm holding the button, it will continue to count up. If we do not reach the preset value and I let go, then the timer's accumulated value goes back to 0. If I hold down the button for the 5 seconds that the timer is set to be active, then it will activate the done bit when we hit 5 seconds, and you'll see now the tank starts to fill up. If I let go of the button, the done bit goes off, and again the accumulated value goes back to 0, so the tank starts to drain. The next one is the timer off. If you remember from our PowerPoint, we remember that the done bit will become active as soon as we press the button. And you'll see what happens. So if I press the button and I let it go, the done bit's active, and now the timer starts counting to 5 seconds. When it reaches 5 seconds, it turns the done bit off. If I hold down the button, the done bit will stay active, and you'll see that the accumulated value remains 0. The timer will only start to count when the rung becomes false. And you can see this over here on the right. When I press the button, it's energizing the rung, which keeps the timer active. And as soon as the rung becomes false, the timer is able to start activating, and when it reaches the preset, then the done bit will be set to 0. The final timer is our retentive timer. Now, like with the others, as long as I'm holding down the button, if we haven't reached the value or if nothing happens, the second that I let go of the button, the accumulated value goes back to 0, and if we were done or the timer was at the preset value, then the done bit would be made false when I let go or turn off the rung. But with the retentive timer, as long as I'm holding down the button, the accumulated value will continue to count up. But when I let go, the accumulated value remains what it was when I let go of the button. If I hold it down and let it get to the 5 seconds, and I let go of the button, now the done bit is latched. So now the tank is going to continue to fill because the timer has reached its set point and has set the done bit to on. It will only go off when I put the reset instruction into the program and I make the rung with the reset bit true. I've attached the reset button to this red button. If I hit the reset, you'll see that the accumulated value goes back to 0 and the done bit goes off. So now the tank is draining again. I can keep pressing the button, and as long as I don't reset the value, the timer will retain the accumulated value. Now I can also reset it even if the timer hasn't finished. So even though we've only gotten to 1.7 seconds, if I press reset now, it'll reset that rung and the timer will go back to the accumulated value of 0. And we can always make these timer set points different. Right now they're all set to 5 seconds, but I can make them whatever we want. If I change the preset of the second timer to 2 seconds for the timer off, then as long as I'm holding the button, it will continue to leave the done bit on, and because it's a timer off, if I let it go, it starts counting. But now, because the timer is set to only 2 seconds, when 2 seconds has elapsed, it will turn off the done bit. If ever you wanted to put in your program a way to change the value of the timer, you would simply just add an instruction to move a new value into the preset. Right now I'm currently manually doing this by typing in a value. So if I make it 10 seconds or 10,000 milliseconds for the timer on delay, then now I have to hold the button for 10 seconds in order for it to activate our output. But if you were to add some instructions to make this automatic, where the PLC can change this value, then we could do that as well. But you can imagine, instead of me manually changing it, what it would look like. I hope that you found this exercise about using timers in Studio 5000 helpful, and I hope that this can answer any questions that you may have had about using timers in your program. Remember, if you have any questions, always feel free to reach out to us. We'll be more than happy to help you out in any way that we can. We look forward to seeing what you do with these projects. Thank you, and have a good day.